Thank you and very good afternoon. First of all, thanks to Dr. Prakash Chauhan, Director IIRS and Steve for inviting me for this session. To Dr. Harish Karnatak and Dr. Arjit Roy for their formal introduction about this course as well as about me. And very good afternoon to all the teachers who are taking part in this wonderful session, which is being organized by IIRS. Today, I'm going to talk to you about astronomy space science in general, but in particular, I will take you to the tour of the solar system by talking more about the planetary science. And as you must be seeing, you are able to see the slides now? Well?
Yes, sir.
Yes, sir.
Okay, so if there is any issue, please let me know, okay?
Yes, sir.
So I will be talking about the planetary science, talking about the planets, their properties, about the solar system, and then take you to some of the missions which has been launched to explore the objects in our solar system, starting with the Chandrayaan-1 mission, going to Mars mission, Chandrayaan-2, and what we can expect in the future. So talking about the planetary science, let me see if second slide is working. Yeah, okay. So essentially what I'm going to talk to you is about an outlook on the planetary science. And as you can see in the slide, the 9 planets in our solar system, as well as few other objects, which you can see it much better over here, where it shows the planets with respect to relative size of the sun. And if you look at this slide, you will say that there are 2 classes of planet in our solar system. One is the inner planets, which is closer to the sun, which is very small in size. And other class is bigger planets, giant planets or outer planets, which is much bigger in size. And these inner planets are essentially much closer to the sun. They are also called terrestrial planets or rocky planets, whereas this outer part of our solar system, consisting of Jupiter, Saturn, Uranus, and Neptune, are called giant planets, gaseous planets, or outer planets. And this picture shows you the size of the planets, or relative size, I should say, but not with respect to relative distances. If I want to plot the relative distances and show Mercury over here, then probably Venus will come somewhere here, Earth will be somewhere here, and then hardly you will see Mars on this slide. So this is not with respect to relative distances, because distances are huge between the planets. Okay. Now, how to remember this order of the planets? There's a simple rhyme, which is used in schools. And oops, when I use this, it doesn't move, is it? So I have to go back and then.
You can use the down arrow.
That is what I'm trying to see, down arrows. Okay. So, the rhyme which says easy to remember, or mnemonics, which we use in our space vocabulary, is to remember the first letter of each planet. And we can say that my very excellent mother just sent us 9 pizzas. That means Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But now, Pluto is actually not a part of the regular solar system, because it is considered as a dwarf planet or minor planet. And that is how, I think it doesn't move, is it? Okay, so Pluto being out of the definition of the planets in our solar system, this rhyme has to change. And this rhyme changes as my very excellent mother just sent us noodles. So instead of 9 pizzas, my mother is giving us noodles, because now we have to confine up to Neptune only. Now, this is a way of remembering the order of the planets, which is easy for kids to remember. And school teachers can actually use this in their schools. Now, talking about planetary science, we also call this as planetary astronomy or planetology or comparative planetary science, which is basically a field which consists of many other fields. And one can say that planetary science is a part of the earth sciences, or earth science is a part of actual planetary sciences. Okay? So it consists of many domains of physics. It includes space science. It includes the way how do you do exploration of the planets. So it includes the whole gamut of rocketry, spacecraft, and things like that, because it includes the exploration of the planets also. Now, how do you define a planet? The definition of a planet, which is now given by International Astronomical Union, consists of three criteria. One, a planet is a celestial body that is orbiting around the sun. That means there should be star and a body should go around it, then only it will be called as planet. The second definition is that planet should have sufficient mass for its gravity to overcome the rigid body forces so that it assumes hydrostatic equilibrium. What it means is that the body should be roughly round in shape. And the third definition is that the planet should have cleared the neighborhood around its orbit. That means there should not be any body around the planet which is roughly the size of the planet itself. And this is the third definition which is not fulfilled by Pluto, because Pluto has a satellite called Charon. This is roughly half the size of the Pluto itself. And that is how Pluto is now considered as a minor planet or dwarf planet. Now, if you look at this picture, where we see these four terrestrial planets, Earth, Venus, Mars, and Mercury, you can say Earth and Venus both are similar size. Mars is roughly half, and Mercury is 1/3 the size of the Earth. But when you compare this with the outer planets, when Jupiter, Saturn, Uranus, Neptune are compared, and certainly Jupiter is the largest planet in our solar system, you say Earth is the 5th largest, and you can fit in almost like 10 Earth into the Jupiter. But if you compare this with respect to Sun, now where the Earth is a small dot lying over here, down. And you can say almost like 100 Earth can fit inside the Sun. So this gives an idea about the relative sizes of the planets among themselves and with respect to the Sun. So this is what we call as the new solar system, where we have 8 planets: Mercury, Venus, Earth, and Mars, which are called terrestrial or inner planets. And then Jupiter, Saturn, Uranus, and Neptune are called giant planets or outer planets. Of course, in addition to this, we have many other objects in our solar system like asteroids, comets, and even what we call objects or planets beyond the orbit of the Pluto, called Humo, Makemake, Eris, which you see it in the next slide much better over here. And here you can also see Charon, the satellite of Pluto. And you can say that it is roughly half the size. Fortunately, our Earth's moon is 1/4 the size, and that's how the Earth is saved. Otherwise, Earth would have been also out of the classical definition of the planets. So you can see there are many other objects in our solar system which are considered as dwarf planets, and they are all sitting outside the orbit of the Pluto. In addition to this, you must have also seen in our solar system, there is a huge belt which we call as asteroid belt. And this is a belt between the orbit of Jupiter and Mars. And there are plenty of them which is lying over here. Of course, there is a huge gap between them, and that's how the spacecraft are able to fly through the asteroid belts. But if you look at them, you will find that Sirius is the biggest of them, which is almost like 1,000 kilometers in diameter. And it almost contains 1/3 of the mass of the whole asteroid belt. And there are, of course, asteroids of different sizes and shapes. You can see here Ida. And Ida, which is something like 50 by 20 kilometer oval shape or potato shape kind of object. And it also has craters on its surface. It has a small moon or its own satellite, natural satellite called Actil, which is hardly a kilometer in size. So asteroids, though they are going around the sun, they also have small objects which is going around them. And it's very interesting to see planets having their satellites. Asteroid also have their own natural satellites. And this is called Eros. This is another asteroid which is called near Earth asteroids because they are closer to the orbit of the Earth. And this is the second largest near Earth asteroid. Though the size is very small, you can say here now something like 30 by 10 by 10 in size. So asteroids are quite irregular in shape compared to planets. In addition to this, of course, comets, which are very, very interesting objects in our solar system. They are very small in size because the nucleus is hardly few kilometers or few tens of kilometers size. But they develop a huge coma which becomes million kilometer long once they come into the inner part of the solar system or closer to the sun. And because of the heat from the sun or radiation from the sun, they start sublimating, and because of which they create a huge atmosphere around that, which is called coma, or the atmosphere of the comets. And that is how the comets are visible. Otherwise, the nucleus of the comet is hardly tens of kilometers in size. And they are also very important because they are not only the messengers from outer part of our solar system. Many of them are first-time visitors into our solar system, but they are also believed to be of cosmogonical importance, probably bringing life to the planet like Earth, or even bringing water to the planet, because they are largely watery bodies. So comets are also very interesting objects, and they are also considered to be the most pristine because they don't spend much time in the inner part of our solar system. They go out, and then once in a while, depending on their orbit, they come into inner part of solar system, then again goes up. So if you study the comets, you can actually come to know about how our solar system has evolved. Now, the size, as I was talking about the comets, can be huge. Here you can see the size of the coma or the atmosphere of comet Holmes, which is bigger than the size of the sun itself. So that's why I was telling you that comet can have an atmosphere which can be millions of kilometers. Let us now look at some of the properties of our solar system and try to see how does it compare in different planets. So first of all, this one which you are seeing over here on the screen is the Earth, which is tilted by 23.5 degrees from its axis. And because of this tilt, only we have seasons on the planet like Earth. Now, if you look at this with respect to other planets, and you see here, you will say that Mars is almost similar in tilt with respect to Earth. Jupiter is almost vertical, hardly 3-degree tilt. Saturn, again, very similar to that of Earth, 27 degree. Uranus, very awkward planet, having a 98-degree tilt. That means its poles are actually looking towards the sun, right? And Neptune, very similar to that of Earth, 30 degrees. But look at Pluto, 120-degree tilt. So that means there are planets which are very weird in our solar system, which has very large tilt compared to what we see in the case of Earth. Now look at Mercury, which does not have any tilt, almost zero. And look at Venus, 177 degrees. That means it is ulta, retrograde. It is moving in a reverse direction compared to any other planet in our solar system. So we have tilt, which shows that all planets have their variabilities. Now look at the mass of these planets. And if you compare them, because they are small in size in the inner part, you can say that Earth, if it is taken as one, the size or the masses essentially of the outer part of solar system is huge. And what we actually look for is that the outer part of solar system actually consists of all the mass of the whole solar system. Jupiter being the highest, then comes Saturn, then Uranus, or Neptune essentially, and then Uranus. And which is almost like more than 400 times the size of the or the mass of the Earth. And if you compare this with respect to length of the day, or basically how long the day is, in the case of Earth, it is 24 hours. But if you compare this with respect to other three inner planets, you say Venus, It's 243, right? 243 Earth days. So that means 120 days day, 120 days night. Compared to Mercury, it is 60, close to 60 Earth days. Mars is slightly closer to 1. It is 1.03, you can say. But look at the outer planets of the solar system. Jupiter, Saturn, Uranus, Neptune. They have lesser than that of the Earth. That means Jupiter almost like 10 hours. So it takes 10 hours for Jupiter to rotate on its axis. Earth said 24 hours. Saturn takes about 16 hours. So that means inner part of solar systems are rotating slower compared to outer part of solar system. Now look at the density, right? And density, if you see, you will find that Earth is having the highest density. That means Earth is the most dense planet in our solar system, with a density of close to 5.5. And if you look at the inner part, you will say that all inner parts of the solar system, that is Venus, Mars, and Mercury, they are all denser compared to outer part of solar system, that is Jupiter, Saturn, Uranus, Neptune. And Saturn has a density lower than 1, because 1 is the density of water, right? So Saturn will actually start floating if you put it on the. Also, if you want to compare how their magnetic fields are, of course, Mercury and Venus doesn't have magnetic field. Mercury has a small magnetic field, but other than Earth, the planets which have really intrinsic magnetic fields are Jupiter, Saturn, Uranus, and Neptune. And if you compare them, you'll find that Jupiter has a tilt of almost 10 degree, which is similar to that of the Earth. Saturn is completely aligned to its rotation axis. So rotation axis and magnetic axis both are absolutely aligned. But look at again the weird planet Uranus. It already has a huge what you call tilt of its axis, and then its magnetic axis is also tilted with respect to the rotation axis. So that means this is a planet which is really weird, because you can see very different magnetosphere of this planet compared to that of any other planet. And Neptune also, of course, it has a huge tilt of almost close to 50 degrees. So tilt of the rotation axis and tilt of the magnetic axis with respect to rotation axis is also very important for a planet, because it governs a lot of phenomena. If you look at the atmosphere of this planets and planetary bodies in our solar system, Earth, we know it is dominated by nitrogen and oxygen. So it is like you can say 80% nitrogen, 20% oxygen, or briefly 78% nitrogen and almost like 19-20% oxygen, and then other minor species. Same is the situation with respect to Pluto. Pluto also is nitrogen dominated. But not only this, the other two satellites in our solar system, Titan, which is a satellite of Saturn, and Triton, which is a satellite of Neptune, is nitrogen dominated, like Earth. But if you look at the two neighbor planets from Earth, that is Venus and Mars, they are dominated by carbon dioxide, CO2. They have a nitrogen which is much smaller in content, something like few percent only. So we have planet Earth, which is nitrogen dominated, but inner to the Earth, there is Venus, is CO2 dominated, and outer to the Earth, Mars is also CO2 dominated. But when you go to the outer part of solar system, Jupiter, Saturn, Uranus, and Neptune, they are hydrogen dominated, hydrogen and helium. That's why they are called gaseous planet, and that's why their densities are much smaller. And if you look at them with respect to, for example, Io, which is a satellite of Jupiter, it is sulfur dioxide, SO2, or even comets, which are watery dominated, like H2O. So that means if you look at the whole solar system, you find different planets having different properties, different sizes, different masses, different atmospheric composition, different tilt, and different length of the day. And this makes each planet absolutely unique in its own sense. Now talk a little bit about the sun, because sun is the head of a solar system, and it is basically the main source of energy for all the planets in our solar system. So this sun, if you want to look at different wavelengths, it looks different. White light, this is how the sun looks like. But particularly in the morning and evening, you will see it little reddish, because it is not that the color of the sun changes, but because the solar radiation passes through the atmosphere, and that creates an effect of having radiation color. You can see it infrared or microwave looking quite different, or during the eclipse, you can actually see the corona of the sun and all other features which I will be talking about, particularly if there are flares happening on the surface of the sun, you see, or the CMEs, which shows a violent activity happening on the surface of the sun. But if you look at the sun in X-rays or EUV, extreme ultraviolet wavelengths, it looks very different. Sun looks extremely violent, particularly if you look in the X-rays. And that means there is always something happening on the sun when you're looking in the X-rays or EUV compared to in the visible. And if you look at the radiation coming out of the sun, and if you plot it as a function of wavelength with respect to irradiance, you will see that the most of the radiation from the sun comes in the visible part of the spectrum. And luckily, we are able to see the visible, because our eyes are sensitive to only visible part of the spectrum. Solar, if you look at the electromagnetic spectrum, it starts from gamma rays to X-rays to ultraviolet to visible to infrared to microwave to radio waves, right? But the maximum radiation of the sun is coming in the visible part, and that is good for us, right? Because we are able to see it, or we are able to see the objects because of the solar radiation falling. But if you look at the other part of the solar spectrum, the maximum change in the sun happens in the X-ray regime or in the radio regime. And that happens every 11 years, and that's why we call it a solar cycle of 11 years, solar maximum, solar minimum. But since the visible part is almost constant, we say that the total energy coming out from the sun is constant, and that is called solar constant. It is something like 1360 watts per meter square. It is the amount of radiation or heat which is coming from the sun continuously 24/7 falling on the earth. In addition to the radiation, electromagnetic radiation, sun also emits charged particles all the time 24/7, and that is called solar wind, which essentially consists of protons and electrons and a small amount of W-ionized helium, whose density is almost like 5 particles per cc closer to the earth, and velocity will be somewhere around 300 to 400 kilometers per second. But then this velocity and density keeps changing when there is violent activity happening on the sun, and that is what we call as solar flares or CMEs. And because of this, there is a change in the presence of Earth's magnetic field. And if you see on the right side of this cartoon, you see the dot here is the Earth, and these magnetic field lines starts bending and forming a cavity which is called the magnetosphere. So magnetosphere is nothing but a effect of the interaction of charged particles coming from the sun interacting with the Earth's magnetic field. Are you able to see this movie?
Yes, sir.
Okay, good. So this is a solar flare which is actually happening on the sun. This is not an animation, this is an actual movie. And this is a movie generated in the time period of October-November 2003, when there were a lot of activity happening on the sun, and that was the most active sun in this century so far, and we call it as Halloween in epoch of flares. And one of them which you will be seeing, you are seeing actually the flares which is happening. You see the bright white light coming out from the sun, which is seen in green color, which is just a color contrast to show the active regions on the surface, and the flares. You see the flash, it just happened. And along with these flashes, which is called solar flares, which emits electromagnetic radiation, they also emit charged particles. which is called, oh, this one you see just now. So there are many violent activity which keeps happening on the sun, and one of them is solar flares, which emits electromagnetic radiation. But in addition to this, the mass is also thrown out from the sun, which is called as coronal mass ejection. And here you will see how the CMEs or coronal mass ejections are ejected out from the sun. You see here, it's all moving. Oops, what happened? I escaped to cell. What happened? It got out. Are you able to see the presentation or no?
I think it has come out of
Okay. Just 2 minutes. Looks like the file size was huge and it was creating some issue. Just 1 minute. Probably I may have to skip that, which could be creating issues for it to run. I will skip this.
Run earlier.
Yeah, but sometimes I don't know, maybe bandwidth issue may be there, which is creating issue. Let me see this time if it goes into the same loop, I will skip. Oh, it's worse. So this is what you're seeing here just now was the coronal mass ejections happening, and these small dots which you're seeing. Oh, I think I will skip this because of the size. I think it is creating some issues. So I will skip that. Start from here. So these particles which comes towards the planet Earth, they are able to enter through the polar regions and cause the phenomena called aurora. So aurora is actually a phenomena which is happening in the polar regions because of the charged particles which enters into the region and interacts with the atmosphere of the Earth. But this aurora is not unique only to the Earth. It's present on all planets which have atmosphere and magnetic field. And here you are seeing this aurora happening on Jupiter and Saturn. And these are actually the images taken by the Hubble Space Telescope, which shows the ultraviolet aurora on Jupiter as well as Saturn. And aurora is not only happening in the visible or ultraviolet. It can happen in X-rays, infrared, or even in the microwave part. So these emissions which are produced in the polar regions, the planets, also is multispectral. It starts from almost like X-rays and goes into the microwaves. So X-rays, ultraviolet, visible, infrared, and microwave, or even the radio wave. I was talking about satellite of our solar system, and one of the very unique satellite of our solar system is EO or IO. It depends upon how do you pronounce that, EO or IO or IIO. And this is actually the most volcanically active body in the whole solar system. It emits almost like 1 ton of matter per second through volcanic activity. And that's how it gets this coloration, because it is largely dominated by sulfur dioxide. And the sulfur has this chain reactions which happens on the surface, and it looks like a pizza. You know, all possible color combinations are there on the surface. And it's very interesting object because it not only important for itself, but it also populates the sulfur and oxygen coming from SO2 into the magnetosphere of Jupiter. Similarly, if you look at the other 3 Galilean satellites of Jupiter, that is Ganymede, Callisto, and Europa, and EO also you are seeing here in with respect to relative size, you can say that these 4 satellites of the Jupiter, which was discovered by Galileo Galilei in 1600 itself, are very important because they are quite big in size, and they're bigger than the size of the Mercury and Pluto. So that means we have satellite in our solar system which is bigger than the size of the planet itself. Okay. And if you compare them with the other satellites in our solar system, natural satellites, then Titan, which I just mentioned that it is dominated by nitrogen, is the second largest. It is a satellite of Saturn. And then when you compare them with respect to Earth's moon, it comes at the 5th place. So the Earth's moon is 5th in size when you compare the satellites in the solar system. And now talking about the moon, let me talk a little bit about the first Indian lunar mission and how we did the exploration of that. So Chandrayaan-1 mission is the first Indian lunar mission, a mission to explore the moon. Chandrayaan, Chandra and Yaan. Chandra means moon and Yaan means spacecraft, and that's how the word Chandrayaan is come. And this is a mission which was launched in 2008, almost 13 years back, right? And after launching on 22nd of October, we reached the moon on 8th of November 2008. It had 11 experiments on board, and 3 of them were actually being flown for the first time on any planetary exploration. And this is the whole spacecraft which you see here with the all experiments, or what we call as payload, sitting over that. And they are all put up here in the bottom with the names. So there were 11 experiments on board. It was truly international in the sense that 10 countries participated. Here you can see it much better. And it also had the moon impact probe, which is sitting on the top of it, which was itself a self-contained microsatellite, and which was actually released after the Chandrayaan reached the moon orbit to land onto the polar regions of the moon. And the SARA experiment is the one where I was directly involved as the principal investigator, which has 2 what you call the sensors, SINA and SIM. SINA stands for Chandrayaan Energetic Neutral Atom Analyzer, and SIM stands for solar wind. And they were actually looking at a new phenomenon which is happening on the sun, on the surface of the moon, due to solar wind coming from the sun impacting, called energetic neutral atom process. So there are many science results which has come out from the Chandrayaan-1, and the most important is of course the discovery of water. It is the Chandrayaan-1 mission which discovered water on the moon. Till that time we were all thinking that moon is bone dry, but Chandrayaan-1 mission really confirmed that the moon does contain water, and it contains a significant amount of water, and a large amount of it is there in the polar regions, particularly in the permanently shadowed regions. There are more than 180 scientific publications which has come out from this mission, and which has validated the lunar magma hypothesis because of large amount of crystal field spire present, mini magnetosphere have been discovered, craters of various dimensions, as well as volcanic vent, which also talks about the volcanic activity happening in the very recent 100 million years or even down to 10 million years. And there are of course many other features which have been discovered, and many of them have made the cover page of various international journals. Here you are seeing them of science and geophysical letters talking about the discovery of water and the discovery of mini magnetosphere on the moon. This is a view which I like very much, which is taken from the terrain mapping camera on the Chandrayaan-1 on 22nd of July 2009, showing how the Earth rise looks like from the surface of the moon. So on the bottom side, you are seeing actually the moon surface, small part of the moon surface, and you are actually seeing the Earth, how the Earth looks like, and you see from the moon. And this is the nothing but the surface of the moon. Let me see whether this one is playing. Is it playing the movie? Are you able to see a movie?
Yes, sir.
Yes.
Okay, great. Very nice. So this is actually how the surface of the moon looks like, taken from the terrain mapping camera. You can see this all spots or dots of various sizes are basically craters. So craters of all possible sizes are present on the lunar surface, from centimeters to meters to kilometers to hundreds to thousands of kilometers. So very big craters we call as basins, like South Pole Aitken Basin. And it of course varies in different places with respect to albedo, depending upon the mineralogy and the mass. So this is how the surface of the moon looks like. And more detailed information, I think Dr. Prakash Chauhan will be talking to you when he talks about the planetary geology. Also, when I was mentioning about the interaction of the sun with respect to the Earth and the moon, so as the moon goes around the Earth, moon passes through the magnetotail or magnetosphere of the Earth, and almost like 6 to 8 days it is inside the magnetosphere of the Earth. But rest of the time it is directly exposed to the solar wind. And this picture is the one which we are knowing before the Chandrayaan-1 mission, which we call it the pre-Sara Chandrayaan-1. That is, the solar wind is coming. This is basically 95% proton and 5% or 4% of helium and helium. Comes and interacts with the lunar surface, get absorbed, and a cavity is produced, which is basically a wake, and there is no particles. This picture has totally changed now because of the new science which has come out from the Chandrayaan-1 Sara experiment, and the picture looks like this. It is totally changed now. We know that there's a lot of things which is happening on the lunar surface. A significant amount of this solar wind which is coming, interacting with the lunar surface, is getting backscattered, but not as protons, but as neutral hydrogen. And it's almost like 20%. That is 1 in 5 particles are backscattered as neutrons. Not only that, this solar wind particles, which has a velocity of about 400 km per second, or you can say energy of about 1 keV, comes and hits the lunar surface and breaks the bonding and releases the oxygen present in the oxides, and that is how we see the sputtered oxygen, which is almost like 4 to 8%. And not only that, at the regions where we have magnetic anomalies, that is the regions where there's a small amount of magnetic field on the lunar surface, the small region, it can produce mini magnetospheres. So that was one of the discoveries from the Sara experiment of Chandrayaan, that mini magnetosphere does get produced by the presence of a small magnetic field on the moon's surface, which deflects these protons coming towards the lunar surface. And that is also changing a lot of things in terms of the albedo and the space weathering on the moon's surface. And on the night side also, there are various phenomena which have now been found, which is feeding these charged particles into the night side, where we are earlier thinking there is nothing present there. And there is a significant amount of plasma processes which is happening on the night side, which is making this studies very important and very interesting, because the moon is not boring for plasma physicists now, because of a lot of processes which happens very close to lunar surface and in the region in the vicinity of the. Talking about the moon, from moon, talking about the Mars, or the Mars mission of India, which we call as MOM, or Mars Orbiter Mission, or we say Indian MOM to Mars. And this mission has really outlived its planned lifetime of 6 months. It is still inactive. It is working in orbit around Mars. It has already completed 6.5 years in March of this year, in 2021, whereas the planned lifetime was just 6 months. So when we talk about planetary missions, though we keep a lifetime of a mission, many times we see that the mission outlived its life, and it keeps on collecting very useful data and providing information. So this is one of such a mission, which is from India, called Mars Orbiter Mission, or the MOM, launched on 5th of November 2013. 2013, remember that, using PSLV, and it got inserted into the orbit on 24th of September. So it took almost like 10 months, from Earth to reach the Mars. So it was a 10-month journey, But after even 10-month journey, it has now been working around Mars for 6.5 years, or close to 7 years, you can say now. Now, there are various experiments on board the MOM mission, which is developed by various ISRO centers. 5 of them, which weighs about 13 kgs. So the whole spacecraft mass is about 1300 kgs. And 3 of these are developed in the Space Application Center in Ahmedabad: the Mars color camera, the methane sensor for Mars, and thermal infrared imaging spectrometers. The Laboratory for Electro-Optics in Bangalore has developed the laminar flow spectrometer. And the Space Research Laboratory at Vikram Sarabhai Space Center in Trivandrum has developed the MANCA experiment, which is called Mars Exospheric Neutral Combustion Analyzer. And this is a time when I was the PI and I was in Trivandrum in BSS. So this, all 5 payloads are sitting at different locations on the spacecraft. You can see the camera sitting on one side looking towards the Mars, along with the laminar flow photometer. And the MANCA experiment mounted with its field of view towards the plus roll axis, because it is looking in the velocity vector of the spacecraft. These are some of the images which has come out from the Mars orbiter mission, particularly the Mars color camera, looking at the Mars at a different season. As you noticed, it has been working for last more than 6 years, so that means 3 Martian years, and that is how it is able to capture the whole view of the Mars in different seasons. And probably Dr. Prakash Chauhan will be covering many aspects of those observations in his talk. And I will just talk about 2 of the major events, major results which came out. One is talking about the evening time exosphere of Mars, which is basically trying to tell how the atmosphere of the Mars changes as you go up in the atmosphere. And we are talking about somewhere around 250 or 260 kilometer to 400 kilometer above the surface of the Mars, where the CO2 dominated atmosphere changes to oxygen dominated. And that too, when you come to the evening side, it has a different variability compared to the subsolar. So that was a very unique observation, which shows that CO2 dominated atmosphere turns to oxygen dominated atmosphere when we reach an altitude of somewhere around 250 to 260 kilometers. And similarly, there was another observations from MANCA experiment on the Mars orbiter mission, which is talking about discovery of superthermal argon in the exosphere of Mars. And why it is important is that if you are talking about superthermal atoms or atoms which are slightly higher energy or basically are heated, and they are in the exosphere, which is a region where the particles don't collide to each other, or atoms and molecules don't collide each other, then there is a chance of their escape. And that is very important, because that means there will be a larger escape rate for the atmosphere of the Mars compared to what we are talking about. So this presence of superthermal argon in the exosphere of Mars talks about that there are species in the exosphere of Mars which have higher temperatures, and that means they will be able to escape faster, which will have implications for the atmospheric escape and the energy budget of the atmosphere. This is, of course, the small satellite of Mars called Deimos, and MOM is able to capture this in frames for the first time in detail. And this MOM became so famous. You know, one of my colleagues from US has sent me this, telling that MOM has now come on the Coke diet. You can see the MOM picture over here. And then once the MOM mission became successful, there were a lot of stories about it. One of this is from the Google, making a doodle of celebrating Mangalyaan after 1 month. So this is October of 24th of 2014. We reached the Mars on September 24th of 2014. After 1 month, Google celebrated it. Amul, you know, which is very famous brand for milk and milk items, and it produced this cartoon called ISRO's Cow Amul Ye Cheez Badi Hai Mars. And even National Geographic magazine has come out on its page the pictures of the Mars taken by the Mars color camera on the MOM mission. And Government of India realizing that it's a rare feat because India is the first country in the world to have a successful insertion of an orbiter around the Mars in the first attempt. And there are many technological feats which were attached to this mission, and because of which Government of India has put this Mangalyaan on the back of the 2000 rupees. Many of you must have already noticed this, right? Now, talking about the next mission, which is the Chandrayaan 2 mission, the sequel of the Chandrayaan 1 mission, but of course it is much more complex and complicated compared to Chandrayaan 1 because it has not only an orbiter like the Chandrayaan 1, but it also has a lander and the rover. And we all know that we had the launch on 22nd of July 2019. And then we got inserted into an orbit around the moon. And then we had a landing on 7th of September of 2019. But of course, it was a very hard landing. So instead of soft landing, and which made the lander not to survive. But the orbiter is working, and orbiter has 8 experiments on board. They are working very well, looking at various features on the surface of the moon, looking at the three-dimensional maps, talking about mineralogy, presence of water, elemental composition, exosphere of moon, and talking about the very tenuous ionosphere, as well as the features in the polar regions from SAR and elemental composition using the class instruments. So these 8 experiments are working very well in providing very useful data. Some of them I will just skip very fastly, talking about how the features of the surface looks like. This is the Sarabhai crater imaged by the Chandrayaan 2 10 mapping camera. Sarabhai, as you know very well, is the most famous scientist of India, and of course the father of the Indian space program. And he is the one which actually started the physical research laboratory, and which grew into later on to the whole ISRO and Department of Space. So there's a crater on the surface of the moon, which is on the near side. So if you really have a telescope, you can zoom and see this Sarabhai crater on the moon. And this was actually imaged by the telemapping camera. And you can see it much better in this image, where the size of this crater is about 8 kilometers and a depth of almost like 1.7 kilometers. This is, of course, taken from orbiter high resolution cameras, talking about how closely you can resolve features on the surface of the moon, talking about various features which could be as small as a few meters apart. These are some very small craters of few meters, very clearly seen from OHRC. And of course, one of the experiments developed in PRL, physical laboratory, is the solar X-ray monitor, which is actually providing unprecedented information about X-rays coming from the sun, and it has a sensitivity almost like 1 to 2 order of magnitude higher than any other measurements being conducted currently in the energy range of 1 to 15 kVs. And it provides such information every 1 second. So there's a lot of good information which is coming out from this mission. What next? We are not talking about the Aditya L1 mission. Aditya, you know, is a Sanskrit word for sun. So it's a mission to study the sun, but a mission to study the sun, not going to the sun, but from L1 point. And L1 point is a point between sun and earth. Let me see if it is there. Yes. So L1 point is a point between sun and earth. So you can imagine that earth is here, this ball. I don't know whether you can see my arrow. And in the center is the sun. So L1 point is a point between sun and earth, in the front of the earth, at a distance of almost like 1% of the distance between sun and earth. Okay? And as the earth goes around the sun, the L1 point will also go around the sun. So you get the uninterrupted view of the sun 24/7, all that. So that's the biggest advantage of the L1 point. It is one of the vantage points at which you can sit and continuously see the sun. As Earth goes around the sun, you also see what is happening in the sun. So this is a mission which is under planning, which is likely to be launched next year. And this has 7 experiments on board, which looks at different wavelengths right from hard access to soft access to ultraviolet to visible. In addition to this, of course, it also has charge particle measurements. Because I was mentioning to you that the sun emits not only electromagnetic radiation, but also emits charged particles. So we have experiments which will look at this charged particle which is coming from the sun towards the Earth, and using this experiments on board. So this is going to provide us a lot of information about the processes which is happening on the sun, how these charged particles or coronal mass ejections are happening, flares are happening, how they are getting accelerated as they move from sun towards Earth, the processes by which the corona is getting heated to very high temperatures of 1 million Kelvin, and what is the kind of distribution of this solar wind charged particles and their temperatures, and how does they vary across the sun, as we go around the sun. So there are many things which is going to be obtained from this unique mission called Aditya L1 in the upcoming solar mission of India. And this will be also very unique because now we have solar activity which is getting picked up, and which will be the time for us to actually look at very energetic processes which happens on the sun. I just mentioned about that. And in the future, we are talking about going to Mars and Venus. Mars, of course, for the second time, but Venus for the first time. And Venus is also a very important planet of our solar system because Venus has some very unique features. If you notice that I was talking about Venus rotates very slowly, but Venus also has atmosphere like Mars or CO2, but its surface pressure is almost 90 bars or 90 times the surface pressure of the Earth. And it has thick clouds in its atmosphere, somewhere around 40 to 60 kilometers, which are dominated by sulfuric acids. And that is why we are not able to see the surface. What image you are seeing here on the right side bottom is not of the surface of the Venus, but it is the cloud sector. We are very difficult to see the Venus surface in the visible. And that's why Venus has very unique features compared to Mars, because Mars has much thinner atmosphere compared to that of Earth, whereas Venus has very thick atmosphere. And therefore, the processes which happens on Venus is very unique. And also, these clouds which I was talking about, they rotate very fast. So we have a super rotation happening for the clouds because the planet takes almost like 243 Earth days to rotate on its axis. But these clouds are rotating around the Venus in 4 days. So clouds are rotating much faster than the planet itself. So in addition to this, of course, once it is closer to the sun, you get a different kind of environment with respect to charged particles coming out of the sun, electromagnetic radiation, and therefore it has not only an atmosphere but a thick ionosphere, and its interaction with respect to the charged particles coming from the sun, giving rise to solar wind ionosphere coupling and interactions, which is somewhat similar to that on the Mars, but it is much more violent compared to that. So Venus is very unique compared to other planets in our solar system, and very unique to study and understand much more. Now, talking about these planets, I will now talk a little bit with maybe hardly for a few minutes before I close down about exoplanets. Exoplanets means these are the planets which are in the other solar system, not in our solar system. Okay? And you must have heard about that there are more than 5,000 exoplanets which have been seen in other solar systems, around other suns or other stars. So in PRL, we started a program to detect this and characterize this exoplanet. And there was a special instrument which was developed, which is called PRL Advanced Radial Velocity Abu Sky Search or PARAS instrument. This is a unique instrument which is developed in India. This is only one such an experiment in India which can detect exoplanets. Okay, so this program started in 2007, and this experiment was developed in 5 years in 2012. And this is how this looks like. Of course, it is very difficult to explain you, but it is all inside this chamber you see. because it has to look at this very faint emission and the movement of the planet, which causes the movement of the star itself to wobble, has to be measured. Okay? And this is all done using this telescope in Mount Abu in Guru Shikhar at the peak, which is in Rajasthan. So we have a telescope of 1.2 meters here. And this is a very unique facility in India because this has a very good, what you call, visibility in terms of seeing, with almost like 1.2 arc second view. And because it has a very large amount of cloud-free nights, one can make observations of various celestial objects in the night time. And this telescope has discovered the first exoplanet discovered by India. Okay? And this is what we call as K2b236. This is how the nomenclature goes. And this has been discovered by IIRS scientists, which has a mass of almost 27 Earth mass, radius of almost 6 times Earth size. And it takes about 20 days to go around its own planet star. Okay? So this, what we call technique to detect the exoplanet for radial velocity measurement is very unique because it can precisely tell you that it is a planet and not a brown dwarf or any other star. It's not any other star which is going around a star or a brown dwarf going around a star, but it is actually a planet. And one can calculate even the density of the planet using this kind of thing. So this is the first exoplanet discovered by India and Indian scientists using the facilities in India. And this telescope facility is now being upgraded. So we have coming up with a 2.5 meter telescope at the same location. So now you are seeing the old one, 1.2 meter telescope and 2.5 meter coming in the back. You can see it much better over here. And this will now be an order of magnitude improvement over what we could do using the 1.2 meter telescope here. So this is still getting commissioned. The building is ready. The telescope is getting installed. It will take about 6 months to 8 months to get it really commissioned to see the first light and then start making observations. So in India, we are not only working on our own solar system, looking at different planets, exploring planets, but looking at the planets outside our solar system also, which you called as exoplanets. And these are very interesting because they also tell us much more about our own solar system and about the planets present in our solar system. Because if you find features which is very different than in our solar system, you come to know that yes, this kind of planet also can exist and can have possibility of life on other planets compared to what we could see or we could explore in our own solar system. So I hope you must have interesting session of understanding the planets in our solar system, the planetary exploration, the programs which India has undertaken, and also the exoplanets. So with this, I would like to thank you all for listening patiently. Thank you very much.
Thank you very much, sir, for such an informative and wonderful presentation. I really believe that our participants have gained a lot of insight into the solar system and the universe in general. Sir, there are a lot of questions we have, and almost all of them are really interesting. So I'll take the questions as much as we can, although I'm sorry that we will not be able to cater to all the questions.
Actually, I have another meeting coming at 5:30. Okay, and so I have to leave in another 15 minutes, maximum 10 to 15 minutes. Huh?
Fine, sir. We will take in 10 minutes of you.
Sure.
So there is a question: how do we measure the distance between galaxies? Is there any method for that?
Distance between the galaxies. See, first of all, actually, distance and time are related when we talk about the large. So when we say I am seeing an object which is 1 billion year old, okay, it is actually because it has taken that much time for it to come, or the radiation from that object has taken this much time to come. And currently we say that universe is about 13 billion year old, because we are able to see the light which must have started 13 billion years back. Or we say the size of the universe is 13 billion years. Basically light year, the distance we measure in the universe is in terms of light years, right? So because we don't talk about kilometers or miles or thousands of kilometers and things like that. So essentially it is basically that the distance and time are correlated, or size and time are correlated. And this is the concept which is used for understanding how far an object is. And if you look at basically, if you look at this objects in the sky, how do you differentiate two objects depending upon their resolving power, right? So, and you say that I have 1 arc-second resolution. So if I project 1 arc-second resolution into the sky, and there are objects nearby, like for example, closer to Earth orbit, like Moon or Sun, I'll be able to resolve it much better. But if I go to galaxies, then probably it becomes more blurred, because I'm not able to do fine resolutions, because the projected space of 1 arc-second is huge there. So that is how the concept of this is used for resolving the distance. Basically, it is an angular size which matters.
Thank you, sir. So there is another question. How do we estimate the composition of atmospheres of other planets?
Okay. One way is, of course, to go there and explore, but which is not possible when we really started talking about it. Other way is looking at the emissions, or looking into the absorption features. So if occultation, or basically eclipsing. So suppose there is a solar light which is coming towards Earth, and an object passes in front of it, and it has an atmosphere. So what is going to happen is, depending upon the species present in the atmosphere, the sunlight will be absorbed in a particular wavelength band. Okay, and that will be unique to the gases present there, because absorption features are very unique to the molecules or atoms. Okay? So once it is there, we can very clearly see that this is coming because this gas is present. So one way of exploring is, or understanding the presence of any atmosphere, is by looking at the absorption features of the atmosphere in the background of a star or the sun itself.
So there is another. Shall we take another 2 questions, sir?
Yeah, sure.
So there is a question. There is a tilt of 23 degrees in the axis of our Earth. Is it in the reference to Sun's axis, as both are spheres? So what is the criteria for deciding the tilt of the planet?
Okay. Generally, planets, if you look in our solar system, all these planets are moving in an ecliptic plane around the sun, more or less in the same plane, but not exactly same. Okay. So if I say sun in the center and Earth is going around the sun, it will create a plane, right? Which we call as the Earth-Sun plane. Okay. Now, when I talk about moon is not exactly in the same plane. Okay. If it is in the same plane, then every what you call lunation in 27 days, we will have a solar eclipse and a lunar eclipse, which is not happening. And this is not happening precisely because the Earth plane in which the Earth is going around the sun is not exactly the same in which the moon is going around them. Okay. So this plane, we decide the tilt with respect to the plane. Okay. In the plane in which it is moving, we decide that tilt.
So the last question.
Generally, all the planets in our solar system are more or less in the same plane with a few degree to each other. Okay, and that's why you will see sometimes occultation of Venus happening or occultation of Mars happening, kind of thing.
Thank you, sir. So the last question: why temperature of corona is more than that of photosphere?
That is $1 million question, which we all are exploring. Why the temperature of the corona is so high compared to that of the photosphere, which is only 6,000 Kelvin. Okay. There are many hypotheses which are being promoted. Either it is basically that there are what we call plasma waves, which is bringing the heat from the photosphere and then releasing it in the corona, or there are microflares which is happening. Now, very recently, using our XSM instrument of Chandrayaan 2, we are even able to see flares which is almost like 2 order of magnitude lower than what it was possible to be seen by any other instrument so far, and which we call as the microflares. And we have also seen flares which is not in the active region. There are flares, microflares, which is happening in regions which is not considered as an active region, means regions where we could see flares. Okay, so that means there is processes which is happening in the corona, which was not seen before, but with the more sophisticated instruments now we are able to see that there are flares of very small magnitude happening, but they are very large in number. So it may not be huge flare like X-class flare where you see violent things happening, which I just talking about and showing you that movie. But these are very, very small flares, which is very difficult to see even. But they are happening, and they are happening in very large numbers. So it could be that the corona is being actually heated by these very small flares, which is present and heating the corona to very high degrees of temperatures of 1 billion. There are many, there are a few other hypotheses which are still being talked about and linked to the processes happening in plasma physics. But still, there is no clear-cut answer to that.